Hello, my name is Jake Seifert. I'm a PhD student of mechanical engineering at Penn State working with my advisor, Dr. Herschel Pangborn. This presentation addresses exciting work completed with collaborators at Purdue University and the University of Texas Dallas on robust successor and precursor sets of hybrid systems using hybrid zonotopes, and is published in Control Systems Letters. Reachability analysis is the process of calculating reachable sets which contain all feasible trajectories of a dynamic system given uncertainties in inputs, disturbances, and the initial state. Reachability analysis is used to provide rigorous guarantees of system performance. For example, if the reachable set does not intersect the set of all unsafe operating conditions, then the dynamic system will not exhibit unsafe behavior. Set propagation methods refer to techniques that iteratively calculate reachable sets. Forward reachable sets can be found by iterating over the successor set, which is the set of states that can be achieved by the dynamics at the next time step, given a state at the current time step, a feasible input, and a feasible disturbance. Backward reachable sets are found by iterating over the precursor set, which is the set of states for which there exists a valid control input to drive the dynamic system into the target set Rk plus 1 for all feasible disturbances. The computational complexity of calculating successor and precursor sets and the growth in the number of variables to represent the resulting sets limits the number of iterations that a computer can achieve, effectively limiting the time horizon that the reachability analysis can be performed. This is especially challenging for hybrid systems, for which the number of variables of reachable sets traditionally has grown exponentially with time. This paper addresses a set of discrete time hybrid dynamics in the form of mixed logical dynamical systems, or MLD systems. MLD systems represent the hybrid nature of the dynamics using auxiliary variables and linear inequality constraints. Under mild assumptions, MLD systems have been shown to be equivalent to a wide variety of other hybrid systems, such as linear complementary systems, piecewise affine systems, and discrete hybrid automata. I like to use a piecewise affine system with only two regions to demonstrate the challenges associated with hybrid systems. The system obeys the top dynamics when x1 is less than 0, and the bottom dynamics otherwise. The initial set is completely contained within the x1 is less than 0 region, and so the first two reachable sets can be calculated using affine methods. At k equaling 2, both regions are active, and so the reachable set can be split and affine methods can be used for both active regions. Again, at k equaling 3, both reachable sets have portions in both regions, and so both reachable sets can be split again, and the number of reachable sets that must be considered doubles. In the case where reachable sets continually intersect both regions, the number of reachable sets that must be accounted for at each time step can grow exponentially, quickly overwhelming memory limitations of a computer. To combat growth in the number of sets, one technique is to over-approximate the reachable set at each time step, though error is case-specific and difficult to analyze. In summary, existing set propagation methods for hybrid systems use some combination of branching and over-approximation with case-specific trade-off between growth in computational complexity, accuracy, and convergence. There exist only a few methods that address exact forward and backward reachability, and these methods are limited in their ability to handle high dimensions and can be computationally expensive. In a recent review of set propagation techniques, the authors again highlight that detecting guard set intersections and avoiding exponential growth in the set representation complexity remains the primary challenge. My co-authors previously addressed successor sets of hybrid systems by developing a novel set representation called a hybrid zonotope. Hybrid zonotopes are an affine image of a factor space by a generator matrix and shifted by a center. A portion of factors are contained within the unit hypercube, a portion of the factors are restricted to binary values, and linear equality constraints on the factors are enforced. The number of variables to store a hybrid zonotope is defined by the number of continuous and binary generators and the number of linear equality constraints. The key qualities of this set representation are that it can represent non-convex, potentially disjoint sets. Furthermore, a hybrid zonotope can compactly represent the union of an exponential number of convex sets with only a linear number of variables. And hybrid zonotopes are closed and have efficient identities for linear transformations, Minkowski summations, and generalized intersections. Using hybrid zonotopes, identities were derived for successor sets of MLD systems that scaled cubically with the state dimension and exhibit linear memory complexity growth. Similar identities were developed for successor sets of linear systems in closed loop with MPC, which also exhibited computational complexity that scaled cubically with state dimension and had linear memory complexity growth. However, these works did not address precursor sets, which are used to calculate backwards reachable sets as well as maximal positive invariant sets. Maximal positive invariant sets are important in the context of closed loop MPC as they guarantee the existence of a control solution for all forward time steps. Because the algorithm to compute maximal positive invariant sets depends on efficient calculation of precursor sets, and because a linear system in closed loop with MPC is equivalent to a piecewise affine system, existing methods use conservative approaches to guarantee recursive feasibility of closed loop MPC. The new contributions of the paper I'm presenting address the precursor sets for both MLD systems and linear MPC. Furthermore, computational complexity of calculating successor sets is reduced from scaling cubically with state dimension to only linear. To accomplish this, a construct called the state update set is introduced. In a few slides, successor and precursor set identities will be given that contain the state update set. The state update set encodes all possible transitions of a discrete time dynamic system over a domain. Breaking it down, a state update set is defined over a domain in the first n dimensions corresponding to the current time step k, and encodes all possible transitions of the discrete time system from time step k to time step k plus 1. This relationship is enforced for all states at time step k within the domain. While this figure depicts individual points mapping to their successors, we will show that we can compute the state update set of hybrid systems without having to do any sampling of individual points. We refer to the domain of the state update set as the projection onto the first n dimensions, and the range of the state update set as the projection onto the last n dimensions. Using the state update set, successor and precursor identities are provided with minor assumptions made in terms of the domain and range sets. For the successor set, the identity includes a linear transformation, a generalized intersection, and a Minkowski sum, while the precursor set is very similar but uses a Minkowski difference and not a Minkowski sum. To provide some intuition, a state update set for a one-dimensional system is shown on the right in purple, with its domain set in green and a reachable set at time step k in black. Note that the reachable set at time step k is contained by the domain set, as is assumed in Theorem 1. The identity first takes a generalized intersection with the state update set and the reachable set at time step k, and then projects the resulting set onto the k plus 1 dimensions. Finally, a Minkowski sum is taken to account for the additive disturbance. If we assume that the reachable sets and state update sets are represented using hybrid zonotopes, and that disturbance sets are zonotopes, the computational complexity of the identities can be derived. The successor set identity, which consists of a linear transformation, a generalized intersection, and a Minkowski sum, improves on the cubic computational complexity of my co-author's previous work and maintains the same linear memory complexity growth. The precursor set, which was not previously addressed by my co-authors, suffers from exponential complexity growth associated with iterative Minkowski differences. The Minkowski difference operator is known to be a challenging set operation, and work to efficiently calculate under-approximations of Minkowski differences is an active area of research. But let us set aside the challenge of Minkowski differences and consider a case without a disturbance, remembering the primary challenge associated with the nature of hybrid systems is to avoid exponential growth in set representation complexity. The identity provided does exactly this, exhibiting only linear memory complexity growth with computational complexity that scales linearly with state dimension. So, if the state update set of a hybrid system can be represented as a hybrid zonotope, then we can achieve the improved computational complexity and memory complexity growth. The question becomes how to generate a state update set for hybrid systems as a hybrid zonotope. The paper first provides an identity for calculating the state update set of a MLD system. The high-level idea is to take the MLD system of interest and to augment the dynamics with a static system such that the first n states do not move. We prove that the one-step forward reachable set of the augmented MLD system is the state update set for the MLD system of interest. To calculate the one-step reachable set of the augmented MLD systems, we leverage the previous work of calculating successor set of MLD systems using hybrid zonotopes. A similar process is also outlined for linear systems with closed-loop MPC, which first augments the system in cost and second, leverages the previous work on calculating successor sets of linear systems with MPC using hybrid zonotopes. To demonstrate the precursor and successor set identities, the paper gives a few numerical examples. The first is of the piecewise affine system shown earlier, which consists of two stable affine dynamics separated by a guard at x1 equaling 0. Forward and backward reachable sets are calculated from the set R3, which is shown in purple. Three cases are generated by considering various combinations of scaling input and disturbance sets. Case 1 has no input or disturbance. Case 2 has no input and has a disturbance. And case 3 has both an input and a disturbance. The figure on the left shows the reachable sets for case 2 in color and case 1 in wireframe. The effect of adding a disturbance causes forward reachable sets to become larger and backward reachable sets to become smaller. For case 1, when there is no disturbance, forward and backward reachable sets have identical memory complexity growth and computation time. When a disturbance is present, backward reachable set memory complexity grows exponentially, while forward reachable sets grow linearly, and computation time significantly increases for backwards reachable sets due to the Minkowski difference. In a second numerical example, we demonstrated backward reachability of the temperature of 6 heated rooms with heaters in rooms 3 and 6. Plotted are the reachable sets projected onto the states for the temperatures in the rooms that contain heaters. The heaters turn on and off using thermostats with temperature bounds which are plotted as dashed green lines. This example is chosen to demonstrate the scalability of the precursor set identity for a system with 8 total states, 6 continuous temperatures, and 2 binary heaters. Comparing the proposed method to existing methods, the proposed method is 600 times faster and represents the set much more compactly with 1/100th of the total generators and 1/20th of the total constraints used by existing methods which explicitly represent 1,125 convex sets. We note that the hybrid zonotope consists of 2 to the 413 convex sets, which is unfathomably large. Though analysis of this set is still possible as many of these sets are empty and existing mixed integer linear program solvers can effectively handle large numbers of binary variables. The final example considers a double integrator in closed loop with a model predictive controller. Determining the maximal positive invariant set of this closed loop system was computationally expensive due to a lack of efficient precursor set identity. The calculation was so challenging that existing approaches instead show how to choose a terminal state constraint such that the feasible space of the model predictive controller is the maximal positive invariant set. This imposes an artificial and potentially conservative constraint on the MPC to gain insight into the region that the MPC will be recursively feasible. On the right, we show a conventional approach, which is to set the terminal constraint to a maximal positive invariant set associated with a surrogate controller such as LQR, shown as the black wire. This guarantees that the entire feasible region of the MPC is recursively feasible. Our approach does not artificially restrict the MPC formulation and sets the terminal set equal to the stage state constraints. Armed with an efficient precursor set identity for linear systems in closed loop with MPC, we calculate the maximal positive invariant set directly, which in this case is a subset of the feasible region. In doing so, we reduce conservatism in our MPC formulation and can verify recursive feasibility of MPC over a larger region, which manifests as the region in red on the left being larger than the region in red on the right. In conclusion, this paper has provided efficient identities for successor sets and precursor sets that rely on hybrid zonotopes and a construct called the state update set. State update sets for MLD systems and for linear MPC were provided, and numerical examples demonstrate the computational advantages of the approach and potential impact, such as reducing conservatism in MPC formulations. I'd like to thank my collaborators at Purdue and UT Dallas, in direct correspondence to my advisor, Dr. Pangborn. Thank you.